So we're now going to talk about how precipitation actually happens on Earth. And I'm going to break it down for you in the form of a recipe. And there's 4 basic steps in this recipe. We need to first cool the air to the dew point. We need to condense water vapor onto nuclei. We then need to grow those nuclei into droplets or crystals that are big enough to fall from the sky. And then we need to bring in more water vapor from the surrounding area to sustain that process and actually get appreciable precipitation. There's a lot that's packed in here, and we're going to walk through each of these steps in some detail to break it down for you so that you understand the physics of what's going on. So we first need to consider water vapor in the atmosphere. And when we're talking about water vapor in the atmosphere, we're going to describe it in terms of this thing called the vapor pressure. What is the vapor pressure? Well, we'll denote it with the symbol E, and it is the partial pressure of water vapor. What does that mean? If you think back to a physics or chemistry class, you'll remember that gases all exert some pressure, and the different molecules in sum contribute to the total pressure. The vapor pressure is telling you how much pressure is exerted by the bouncing around of water molecules in the atmosphere in particular. If we think here, how do we talk about pressure? This is something that you'll need to know throughout this class. Pressure is, in SI units, commonly described with this unit called the Pascal. And the Pascal is denoted PA, and it's equal to a Newton per meter squared. So it's describing a force per area. That's what we mean when we talk about pressure. And the vapor pressure, there may be there's a term, and that describes how much water the atmosphere can hold, how many molecules can be at a particular pressure and temperature before that water starts to basically condense out of the atmosphere and become a liquid. And that's called the saturation vapor pressure. So that is the maximum thermodynamically stable vapor pressure just before you would start to get condensation and liquid water forming. So this is called the saturation vapor pressure. And you'll commonly see it denoted with this symbol E and raised to a little asterisk. One other common term that you're probably familiar with is the concept of relative humidity. Absolute humidity describes the mass of water per volume, but we commonly talk about relative humidity, and the relative humidity means how much water is there in a particular parcel of air relative to how much water there would need to be to get to the saturation vapor pressure at that particular temperature. And so this is described simply as the ratio of the actual vapor pressure of the air divided by, at that temperature, the saturation vapor pressure. Now, where am I going? We need to bring this back to precipitation. I'm going to draw a plot for you that describes the relationship between vapor pressure and temperature. And it's a key point in this recipe for precipitation. So here, we're going to draw some axes. On this axis over here, we're going to have vapor pressure. And the units of this will be kilopascals, kPa. And we'll go from 0 up to 10 here. 0, 5, 10. On this axis here, we're going to do temperature in degrees Celsius. And we're going to go from -40 here to 0 and then out to 40. I'll try to draw this. So what is the relationship between vapor pressure and temperature? Well, it looks like the following. A nonlinear increasing curve here. So something like this. This is for a particular temperature, the saturation vapor pressure. So there's two things that could go on. We could have a parcel of air on Earth's surface that's not saturated and may sit somewhere here, for example. The distance, the vertical distance between the actual conditions of this parcel of air and the saturated vapor pressure is known as the vapor pressure deficit. So that's how much pressure of water would need to increase at this temperature to saturate the air. Then there's another term here that you have commonly heard of, and that's the following. Imagine that we were to take this parcel of air, keep it at the same pressure, but just cool it down. And so we're cooling it, we're cooling it, we're cooling it. We're moving horizontally in this plot until we reach the saturation vapor pressure line. This is known as the dew point. So this is the temperature at which this actual parcel of air would have to cool to reach the saturation vapor pressure. Now, there's one takeaway from this whole plot, and that's an important thing to remember, and that is that as you get warmer and warmer, the vapor pressure required for saturation goes up and up. Another way of saying that is that warm air can hold more water vapor. And this is an important point, so I will just write it down. Warm air can hold more water vapor before it gets to the saturation pressure.